Hey guys, Mr. Betts here. I want to continue talking about Riemann sums, but I want to remind you that our ultimate goal is to be able to evaluate a definite integral. Remember, we're looking to solve the area problem, and right now we can use Riemann sums to approximate an area between a curve and the x-axis, and I want to look at how we can take that further, make it more accurate to the point where we're actually evaluating the exact area. So, just a quick refresher: Riemann sum is a sum of sum. It's a sum of areas of rectangles. So, the areas of the rectangles that I have drawn here are going to approximate the area under the curve. I want to point out a couple of things that I did here intentionally. One is that the widths of the rectangles are varying. So some rectangles are wider and some are narrower. And in a Riemann sum, that's okay. If we're looking at data and we're using data that's given to us, sometimes we might do something like this because we're kind of forced to. Other times we might do it for practical purposes. But this delta x here, which represents the width of each rectangle, that can be different for different intervals, or subintervals, I should say, for a Riemann sum. The other thing I want to point out is that the location along each subinterval that I chose to use for the height is different. So I used somewhere kind of in the middle. I used a left end point. I used a right end point. And so the important thing is that the x value that we're plugging into the function to get the height is somewhere along each subinterval, but it doesn't matter where. It could be a left end point, it could be a right end point, or anywhere in between. Now, to generalize things, we're going to stick with one or another so that we're consistent and we can write out formulas. But in a general Riemann sum, it doesn't matter how wide the rectangles are. It doesn't matter where along each subinterval we use the height, but we need to make sure we're using both for each one. So the idea here is that to make this more accurate, we're going to make the rectangles smaller. Now, obviously, by making the rectangles narrower or skinnier, or however you want to think about it, by decreasing this width of the rectangles, then the error that we're going to get, either over or under, is going to get smaller and smaller. And not only is the error for each rectangle going to get smaller, but then overall the error that we are off in total is also going to get smaller. So the idea here with this limit is basically saying that the maximum width of a subinterval is approaching zero. So I drew this obviously with non-zero widths, but as we add more and more rectangles, let's say I just take this rectangle and split it up into two, so we're using two different heights here now, and we're just taking the rectangles and making them narrower and narrower, our error is going to get smaller and smaller and approach zero, and now this is no longer an approximation. Okay, so remember, this limiting process here is a process that could go on forever, but the idea is we're making the rectangles really, really, really skinny. And by doing that, we're making our error really, really, really small. And now we have a way to evaluate the definite integral. Now, here's the problem with that. We can't find the area of infinitely many rectangles. And if you think about what we would have to do to make this limit work, is we would need infinitely many rectangles, because if the widths are really close to zero, we're going to need a whole lot of them to get the entire width of the interval. So this is where formalizing the way we're going to do this comes into play. So I'm going to kind of simplify this limit here rather than thinking about the widths of the rectangles going to zero. Rather than that, I want to think about the number of rectangles we're going to use. In order to do that, though, we have to be very careful about formalizing one particular thing. If I just say that the number of rectangles is getting really big, that doesn't necessarily mean that the widths of all the rectangles are getting really small, because remember, the widths can be different. So we could have infinitely many rectangles, but we could have one rectangle out here in the middle that's just never changing. And obviously, this is not going to give us an exact answer. Okay, so we could have infinitely many rectangles along this part and along this part, but as long as we have a rectangle here that has a non-zero width, this doesn't work. So in order to account for that, we're going to do something we talked about before, and we're going to say this delta x here is going to be the same for all of them. All right, so instead of having each interval allowing it to be different widths, we're going to say that the intervals are all going to have equal width. And if that's the case, the more rectangles that we add to improve our approximation, then the narrower the rectangles are going to be. So then, as n approaches infinity, the widths of the rectangles are going to approach zero. Okay, so that's going to look like this. Notice that the I that I had here on the delta x is gone because delta x is going to be the same for every single rectangle. All right, so by standardizing the widths of the rectangles, now we can just say the number of rectangles is going to go to infinity, and that's going to force delta x to approach zero. I also want you to keep in mind that to find delta x, we're going to take the width of the integral, the width of the interval, sorry, for the integral, and we're going to divide by the number of rectangles. So, sorry, I forgot the x there, delta x. So as n gets really big, so as that approaches infinity, the width of the interval divided by infinity is going to approach zero. So effectively, this is also going to make delta x approach zero. We wouldn't have to write that as part of our limit, but that's what's going to happen. Okay, so now by doing that, as we add more rectangles, now you can see here that this is a little bit more uniform. And the areas of the rectangles here are going to approximate. Now, I'm just drawing rectangles that roughly approximate the height. So the last thing that we want to look at here is the x value that we plug in. We want to make that consistent for each interval so that we can use a formula. So rather than just saying we're going to pick some point along each subinterval, what I'm going to do here is I'm going to say we're always going to pick, say, the right endpoint. And if we always pick the right endpoint, then what we're doing is we're plugging this x coordinate in here to the function to get the height, and we're going to keep doing that. So what we're doing here is the RRAM approximation, but we're doing it with more and more and more rectangles. All right, so one last thing. This is something that I've done before here, but just assuming that we're going to do RRAM, the very first x value that we're going to plug in here for f is going to be a plus delta x. Okay, so keep in mind we're not plugging this point in here, but the width of the rectangle here is delta x, so we're going to start at the left end point and add on delta x. Then the next one is going to be a plus 2 delta x. Then the next one is going to be a plus 3 delta x. Then the next one's going to be a plus 4 delta x. And you'll notice a pattern here. These are all in the form of a plus something times delta x. And that something is starting out at 1, and it's going to go all the way up till we get to b. And when we get to b, that is going to be an n there, because a plus n delta x with delta x being b minus a over n is going to be the same thing as b. Okay, so lots of stuff there, but what this tells us then is we can essentially use the RRAM formula. So I took the delta x that was back here and I moved it out because it doesn't depend on I, so I can move it out of the sum. And basically what I did here is I set it up in a way that we can use the RRAM formula. With this and everything else that we've done, now we can actually start to evaluate some particular definite integrals. We're not going to be able to do many yet. We're not going to be able to do definite integrals with like the sine function or the cosine function or e to the x, but we are going to do certain lower powered polynomials. We're going to be able to do that with this. But another thing we're going to want to do is basically take limits that are more or less in this form and say that's equivalent to a definite integral, or a definite integral and say that's equivalent to some particular limit. So for now, our goal is basically to take a definite integral and write it as a limit, or take a limit and write it as a definite integral.